distance. And you can see that that's now starting to get to be kind of far away compared to the size of our own planet. This is starting to feel a little bit more like we're really out in space. And the vast majority, the overwhelming majority of spacecraft that humankind has sent away from Earth have gone to geosynchronous orbit or to some lower orbit. But now let's put this in a little bit larger perspective. Let's bring the Earth down here, reestablish geosynchronous orbit, and now let's bring the Moon in and put it up at the distance that it belongs. So now the Moon is here about 250,000 miles away from Earth, or 30 times Earth's diameter away. And you can see most of the satellites that we send out, they're not even getting anywhere near the distance to the Moon. So spacecraft that go beyond the Moon are really, I think, pretty special. And in fact, Dawn will pass the Moon's orbit the day after it launches. And in fact, in just a little bit more than half a year, it'll be 400 times farther away than the Moon is from Earth. It'll be at that time about the same distance than the Sun, a little bit farther than the Sun is. And I think that's pretty cool when you think about it. When you think about the Sun, the same Sun which has shone down on our planet for 4.5 billion years, the same Sun that's responsible for all the energy that we have on the planet, or most of it anyway, and that has influenced us, in so many ways, not just physical but culturally. To be able to send spacecraft out beyond that, I think, is really something remarkable. And in fact, during its mission, Dawn will be almost 4 times farther than the Sun, 1,500 times the distance from the Earth to the Moon. And in fact, on a previous project I worked on, when the spacecraft was on the other side of the Sun, as corny as it actually sounds, went outside and blocked out the Sun with my thumb and thought, gosh, again, humankind, this is something that all of us do. We've got a spacecraft out there on the other side of the Sun. I think that's something really remarkable, and I think that's a lot of what many people, I think, at JPL find to be so rewarding about working on things like this. So how are we going to get out there? Well, we're going to start with a rocket. This is called the Delta 7925H, and has 9 strap-on solids down here that will work with the first stage to get the rocket off the launch pad and partway into space. And then this part will drop away, and the second stage will carry the third stage in Dawn up to low Earth orbit, where it'll spend just a few minutes. And then the second stage will finish its job and release the third stage that'll send Dawn out on its way, and then Dawn will take over, do the rest of the mission on its own. Of course, it hasn't launched yet, so I'll show you a movie from a different mission. There's a sort of a space geek requirement that you have to show a video of a launch. This is from a JPL mission that went to Mars. And here's a camera on the rocket looking down at the pad, and you can see the bright glow from these solid rocket motors as the rocket lifts off from the ground. And up here, you can see the shadow of the rocket's contrail. It's the shadow of it on the ground at Space Launch Complex 17 at Cape Canaveral, the same place from which Dawn will launch. And now here, a little bit into the flight, some of these solid motors are going to fall away. There go some of them. There goes some more. A little bit later, now we're on a camera here looking down this way, and we'll see the first stage separate from the second stage. There, the engine is still firing. It's going to tail off in a second. There it stopped, and now this whole stage falls away. It exposes the second stage motor. This thing will fire up and push itself away from that. Now we'll see a shudder in a second. There it shuddered as the nose cone or the payload fairing falls away, and there it goes into the background. And now we're on a camera looking up toward the third stage spacecraft. It's spinning it up, pushes it away with springs, and there goes the third stage and the spacecraft. Excuse me. And for you amateur photographers, I'll give you a piece of advice, and that is don't let a spin rocket get in the way of your subject. That's just bad luck. But it turns out it doesn't matter because the signal from the camera is going to be lost before the third stage fires anyway, so that's okay. So the rocket then has put the spacecraft up into space, and now we'll continue with another view of the mission. So here it is after having separated from the launch vehicle with the solar arrays stowed together. Let's take a quick look around the spacecraft. There's again the ion thruster. There's one underneath there. Here's another on the back. And now we're going to zoom in and look at how the solar arrays are held together. The people that made this animation, I think, are of the opinion that the most fascinating thing about spacecraft is how solar arrays are opened up. So it turns out they're held together, held closed with a cord that has tension on it, keeping springs from opening the solar array. And a mechanism here will release the cord like that, and then the springs on the solar array will allow it to open up. And there are springs on these joints here pushing the solar arrays out so that then they can be fully exposed to the sun, and this guy can convert its sunlight into electrical power and a nice reflection there of its home planet excuse me, as it's about to leave. And so this will happen before we even hear from the spacecraft after launch. And then the operations team will spend a few months checking it out, and just for fun, here's Orion in the background, belt and sword. So we'll spend a little while checking out the spacecraft, making sure that it's operational and ready for its journey through the solar system. And a few months after launch, we'll fire up the ion propulsion system. So here's a close-up of the thruster, and you can see a little bit of gimbaling there, repointing it. The engine comes on. My pet chameleon's happy with the glow there. And then the spacecraft begins its propulsive journey, or its powered flight, on out to Mars and beyond to Vesta. And so it will spend thousands of days thrusting in order to accomplish its mission. Excuse me. And what it's doing there is reshaping its orbit around the sun in order to be able to get up to Vesta and drop into orbit around it. So there's Vesta as the spacecraft is approaching. So the spacecraft will continue operating its ion propulsion system to bring it down into orbit. And this has kind of a funny view on this projector. It almost looks like raindrops hitting the surface. I don't think that's exactly going to happen. In fact, I don't know what we're going to find when we get there. I think whatever it is will be much more intriguing than any artist can imagine. But it will be revealed by the spacecraft using its instruments to scan the surface to make the sort of measurements that we talked about earlier, this comparative planetology, understanding the surface and the subsurface, really understanding how this thing works as a planetary-type body. And then when it's finished, it'll just have a last look back as it turns on its ion propulsion system again, leaves Vesta to begin its journey to Ceres, where it'll do the same sort of thing. And, excuse me, again, this kind of mission would not be possible without ion propulsion. In fact, it wouldn't even be possible to rendezvous with just one of Dawn's targets, either one of the targets, if we used a conventional propulsion system within NASA's constraints. So if we didn't use ion propulsion and we just wanted to go to Vesta, which is actually the easier of the two targets to reach, we would need something like 2.5 tons of chemical propellants instead of just a few hundred pounds of xenon. Really a tremendous difference. In addition, we need an entirely new spacecraft structural design. And I mentioned earlier, we take advantage of the fact that Orbital Sciences Corporation has a spacecraft structure that can work with the amount of propellant that we're using and the size of the tanks. But we would lose that if we had to use a conventional propulsion system. In addition, we'd have to use a high-energy version of the Atlas V rocket instead of the Delta II that we're using. And to give you a sense of the scale here, this is the height of the Delta II rocket. This is something else whose height you may sort of have a sense of. And that's the height of the Atlas V that would be required if we were just going to go to Vesta with conventional chemical propulsion. And it would truly be impossible with current technology and currently available rockets to design a mission that would go to Vesta and Ceres without ion propulsion. So this really makes a huge difference in what we're what we're planning to do. So now let's take another look at where we're going. There's another view of the solar system. So here's again the sun in the center. This is the orbit of Earth. And here's about where Earth will be this summer when the spacecraft launches. And as